Dr. Awofisayo. I lecture and work in University of New York. And so today we want to look at water analysis. Some of our members in a research work in Bioscird Laboratory. And so today, as a preamble, we like to note that water is essential to life. And about 97% of the Earth's surface is water. Less than 3% of Earth's total supply of water is fresh water. And polar ice and inaccessible groundwater makes half of this 3% that we're talking about here. In the developing world and also in developed countries, water is becoming progressively polluted. Every form of water seems to have its own contaminants on a very challenging way. So the source of water includes industry, sewage, treatment plant, household, decaying plant and animals, litters from cigarette butts, pouring of oil down sinks, and all the rest. So all of this account for the contamination that we have in water. So these are washed through stormwater system into drains, and they run off into creeks and rivers and eventually the ocean. So when we say water is becoming progressively polluted, that is what we mean. And everyone can help reduce water pollution. You and I can help reduce water pollution by following the Environmental Protection Act of 1994 that adopts an environmental stewardship approach, that all of us are responsible for the pollution we have, and that if we take a cue, then we can have better water supply. So our goal includes ensuring our waste does not end up in our waterways. And so we can see how progressively water is being polluted. So by way of introduction, water quality describes the condition of the water that we have at hand, and it has to do with the source and the purpose for which we intend to use it. So the quality reflects its physical, chemical, and microbiological characteristics. And so we want to match that very closely with the suitability for the intended purpose. Water can be used for different purposes, and we're going to look at that briefly before we go into talking about analysis of water. So is the water for drinking? Is it for swimming? Is it for washing? Is it for industrial purposes? So this water we want to analyze. Is it for any of these or some other uses? So this picture here shows someone who is drinking the water. He actually needs his water drinkable. He wants it to be table water. And then this person is here need it for their domestic use. And so use of water, industrial, recreation, home, power, agriculture. What do you need the water for? So as an analyst, I want to analyze the water and give the parameters that we need. At this point, we want to talk about water-specific guidelines. There are some guidelines by organizations like World Health Organization, Canadian and Australian drinking water guidelines are also available. They talk about, for instance, E. coli should not be detected in a 100 ml sample of drinking water. So for every 100 ml of drinking water, we don't want to see not even one E. coli at all detectable there. And if it is, then immediate action has to be taken to minimize human risk. And the E. coli we're talking about here, we are not even streamlining the source, fecal or not. All we're saying is we don't want to see E. coli in our drinking water. So specifications based on all these guidelines are based on realistic data, e.g. E. coli are commonly found in the face of warm-blooded animals in high numbers. Therefore, their presence in any water source indicate that the presence of fecal contamination and potential enteric pathogens are available in that water source. So water analysis therefore is premised on realistic backgrounds, and these guidelines by these organizations are also so presented, are also of serious consideration. And so when we want to find out in very comprehensive microbiological tests, we want to look at the biochemical characteristics of these organisms. and then use that to design procedure or protocol for them, so that the water can actually be said to be pure. Submission or report. So now let's talk about sources of water, face water, like we have in lakes, streams, river, pond, and ocean. Then we have groundwater too, shallow well, deep well or boreholes. And then we have rain or storm water. So this picture here just describes water that we have around us, the water types of water. We can classify water to be water or saline water based on dissolved salts. Like in the oceans, we have saline water, and we don't want saline water. Nobody likes to take that because of the risk it poses. So all this calcium, magnesium in water makes them hard, and so when those are not there, we call it soft water. So water quality indicators. What are water quality indicators? Biological, as in do we have algae, bacteria in that water. Then physical indicator, the temperature of the water, the turbidity, clarity, color, salinity, suspended solid, etc. These are physical indicators. Then chemical indicators, the pH of the water, the dissolved oxygen, biological oxygen, demand, nutrients, including nitrogen and phosphorus, organic and inorganic compounds, including toxicants. If all of these are permanent, then we're going to raise an eyebrow, so to say. Then aesthetic indicator, does it smell? Has it taint, color, floating matters? Then radioactivity, do we have alpha, beta, and gamma radiation, emission, or particles in there? Okay. So indicator of water quality can be physicochemical indicators, dissolved oxygen, pH, temperature, and salinity. Then we have insecticide, herbicide, or metals present in that water. Then biological indicators, the fauna and flora in the waterway, and also present some macroinvertebrates and benthic algae in the water. So at this point, I'd like to say that the source of the water will alert an analyst as to what to expect and what to analyze for, what to pay more attention to in that analysis. So habitat indicator, as we have here, fringing or riparian and in-stream habitat. Are there falling trees in the waterway? Okay, are there scoring and bank erosions, into the water and all of that? So all this information can help an analyst, design the analytical protocols to cover, detecting most of these things that can be of concern to us. So then the flow indicator is also important. Changes to flow causing aquatic ecosystem degradation can also affect water quality, and so an analyst will need to put that into consideration. Government sometimes create river basin or regional aquifers, and this can affect the water quality, and so the analyst must have to also read and capture all of these parameters. So some environmental problems and contaminants that we have by way of a theoretical presentation include, as in when fertilizers are used extensively in that environment, you're going to have enough of phosphates and nitrates in the water, and this has to be detected. Then pesticide and herbicides too are also what can give us concerns, because they present some dimethylamine salt, paraquat, glyphosate, etc. Then in domestic operations, dishwashing detergent can also present some contaminants, and this includes sulfate esters and fatty alcohols. So this picture here shows us that even in rainwater, with all these fumes and dust going up there, rainwater can actually still bring all of this down and causing the pollution we'll be talking about. So contaminants, because as an analyst, we actually want to present our results, picking the salient contaminants to see whether the levels at which they appear in that water is what we need or not. Surface water contaminants. Fresh water is a scarce and valuable resource, one that can easily be contaminated, and that is a fact. Once contaminated, the extent to which it is can be considered polluted. So fresh water is difficult and expensive to restore, because if all of these fertilizer-based organics are into the water, then for us to now remove them, detect them, remove them, is quite expensive. And more expensive if we don't remove them and we consume them or use them for whatever purposes, and they cause a breakdown, whether in health or in some other sense. So these pollutants have different environmental effects. Excess nutrient, for instance, may result in harmful algal bloom and hypoxia, both in river and coastal seas. And once there's hypoxia, the animals in the rivers die, and a lot of stench dwells under the ground, or in cracks and spaces between rocks and sediments. Most companies actually exploit this for their water production. So most groundwater comes from precipitation, and when it rains or snows and soil becomes saturated, water percolates downwards to aquifers and replenish the groundwater supply. So groundwater contamination occurs when pollutants such as gasoline, pesticide, herbicide, and all this stuff, all these detergents flow down into the shallow well or even the borehole, and causing contamination. So as analysts, we must be poised to be able to detect this. And it can also be found in there. Then pesticide, herbicide, insecticide, oil and gasoline, household products, paint thinners, swimming pool chemicals can be found there. And so our design must capture all of that. So other compounds such as nitrate and nitrite, volatile organic compounds, chloride, fluoride, as dissolved salt, cyanide, sulfate, radionuclides can be found in borehole water or underground water. And so the analysis must be comprehensive enough to capture all of that. So going to rainwater harvesting is currently being practiced in southern Nigeria. Okay, the growing awareness of water conservation and stormwater runoff issues and desire for self-sufficiency in water supply has made so many communities to look towards rainwater as their source of water supply. But the contaminants must also be so the consumption of contaminated water from storage tanks, the tanks that this rainwater or any other water that is put, is also important. And wind-blown dirt, leaves, fecal droppings, and all of that are common with rainwater, and they can pose. And see the roofing sheet here, the material with which it is made. This looks like asbestos, and as water washes through this asbestos roof or zinc roof, whether Cameroon or whatever, or rusted or clean, it gets into the container with which it is contained, collected, and with that, the quality of the water affected. And an analyst has to consider all of these things and give a robust analysis. Wastewater is the polluted form of waste of water generated from rainwater runoffs and human activities. It's also called sewage, and so the contaminants in this are also members from materials and chemicals washed into storm drains from street to street, gutters, neighborhood, industrial sites, parking lots, and construction sites. So all the metallic stuff here and there actually get into stormwater. So improper disposal of used oil, which include oil leakages from cars, contributes significantly to stormwater pollution. And then fires on bitumen, and as rainwater falls there, everything swept into the source where people collect them for whatever use they want to put the water, such as copper, lead, and zinc, hydrocarbons from petrol and oil, pesticide, pathogenic bacteria and viruses, trace organics such as phthalates and surfactants are always present in most of the different sources. Imagine what the floor here will be, and then you can see this local oil industry, and then you can imagine the spillage and water washing all those things off. So that's what we're talking about. That water quality is very important, and the role of a public analyst safeguarding the health of the populace in every community is also very important. People just buy water and drink. Village authorities are actually trying, but how much can they do? So you can also see what we had here is actually very faulty. You can see tires, heaped up here. They can be recycled, and of course, all of this find their way into our different sources of water. And no matter how we have treated it, if we don't go to all lengths to ensure that what these have contributed to our water is handled, whatever the use to which we are putting the water, whether drinking, swimming, agriculture, a lot of things can be recycled, and all of this impinge on our health and our economy.